Yes, here we go again. We're back again, live and direct with chemistry this time around. I am Adeyemi Abiodun, the lead tutor at 300 Plus Academy. Okay, what we have for you today is chemistry alternative to practical. We have a couple of questions which we are to attempt, and which is a probable question for your GCE General Certificate exam. Okay, but before we go into attempting question, what we want to quickly do is to do a quick run through of what practical chemistry, or rather practical beautiful chemistry entails. Okay, very quickly, when we talk about practical chemistry, it's actually into two broad categories. We are looking at quantitative analysis, as the name implies. quantity Quantity, when we say quantity, we want to measure amounts of substances. We want to look at volumes. We want to look at things like moles. But that aside, we also have qualitative analysis, where we are trying to, based on certain qualities, we are trying to identify ions of matter. Okay, without much ado, talking about quantitative analysis, there are two approaches to this. We have volumetric analysis, where we deal with volumes. We try to analyze volumes to get masses, moles, volumes, concentrations of acids, bases, and all of that. And then we have the gravimetric analysis, where what we do is about direct mass measurements. It's about direct mass measurement. That's talking about gravimetric analysis. Okay. Also, under our quantitative analysis, there is what we call titration. Titration is basically a method under volumetric analysis. It's a method we use in analyzing volume. And what we do here, you recall that most of our titration is actually based on reaction between acids and bases. The acid is actually in the burette, and then the pipette, we use that to measure volumes of bases, fixed volume of bases, usually 20 or 25 cm cube. So what we do here is that we run the acid into a mixture of bases and indicators. I'm going to talk about indicators much later, so that the acid and the base, they react in a neutralization reaction. And as you see, what you have on the board, I said, until there is complete neutralization. The point of complete neutralization is usually what we call endpoint, or the neutral point. The burette is usually in the acid, and the pipette is usually in the base. What does this volumetric analysis mean? Let's say we have a situation where we have HCl, which is a strong acid in the burette, and let's say we have sodium hydroxide, which is a strong base. We've pipetted this. We have this in the pipette. So what we basically do here is very simple. I'm going to pipette the base. That gets into a conical flask. Okay, that gets into a conical flask. I'm going to add 2 or 3 drops of indicators. This is my base. I'm going to add 2 or 3 drops of indicators. Now, the indicator is going to have a color in the base. Then I'll run my acid. I'll run my acid from the burette into the mixture of the indicator and the base. So when I do that, what I expect is that now that I have my base and indicator now, if I should now add my acid to this, I expect the acid now to kick out the indicator and instead react with the base, so that it gets to a point where all of the acid I'm adding from the burette reacts completely with all of the base that I have here. At which point, a single drop of acid, once I had now, if any of the base is no longer available, the acid is then going to react with the indicator, giving us another color, at which point we talk about end point or neutral point, because at that point we are going to experience color change. Take a look at it again. When I have my base and indicator, there is a certain color I am going to have here. But the moment I start to run in my acid into the mixture of the base and indicator, the acid begins to react with the base until a point is reached where all of the base had reacted with the acid, such that if I had a single drop, a drop or two drops of my acid from the burette, is basically going to now have to react with the indicator now, such that indicator plus the acid is going to give us another color. So what we basically do in titration is to run our acid solution from the burette into a fixed volume of pipetted base plus indicator in the conical flask, taking note of color changes as those indicate our endpoint or point of complete reaction, or what we call neutral point. So that is basically what practical chemistry is all about. We want to analyze volumes so that we can tell quantities such as volumes, masses, moles, volumes, concentrations, and also we have qualitative analysis, where what we want to do is to identify ions. Now, in this quantitative analysis, what are the things we need to learn? We need to learn, okay, what are the precautions? We need to learn what are the precautions that we need to take in, filling our acids into the burette, and also in pipetting our base. We also need to learn about indicators. We need to learn about indicators, their colors in the base, their colors in acid, and of course, their colors at the end point. And also, we then need to deal with the calculations that ensue. We need to deal with the calculations. If we do these three, at least we'll be sure of 18 to 20 marks from the 50 marks. And then by the time we deal with the qualitative analysis, of course, we should be sure of another 18 to 15 marks. So what we are now going to look now are the precautions, as you see displaying on your screen, the precautions we take in carrying out titration. You can see that on your screen now, the precautions we take in carrying out our titration. We're not going to waste much time on that. So that the next thing we want to look at now is indicators. Okay, that's about the precautions you need to take. Now, talking about indicators. Indicators are substances which change color in the presence of an acid or an alkali. Normally, indicators have their own color, but in the presence of an acid or an alkali, they change color. So that's what indicators are. And talking about our indicators, we have our litmus paper is the first one. The color in an alkali is blue. The color in an acid, red. At neutral point or at end point, no color change. Take note of methyl orange and phenolphthalein. For methyl orange, when we pipette a base, let's say this is my conical flask. When I pipette a base and I have a base here, okay, and I add 2 or 3 drops of indicator, let's say I'm adding methyl orange. The color of methyl orange in a base is actually yellow, so that by the time I begin to run in my acid, recall I told you that when I start to run in my acid now, my acid is going to react with the base in a neutralization reaction, so that at the end of the reaction, acid plus base, we're going to have salt, which is neutral. So the color of my methyl orange at the neutral point is pink. That is why when we carry out titration and we use methyl orange, we say it changes color from yellow to pink. It changes color from yellow to pink in that first we have the indicator added to the base. So the color of the indicator in the base at that time, that's talking about methyl orange, is yellow. So at the end point, when the acid had reacted with all of the base, what we are going to have is then neutral. So color in neutral solution or endpoint. Then we talk of the color of the methyl orange changing from yellow to pink. But if we then continue to add more acid, such that what we now have is just acid and then the indicator, we talk of red. So this is what we are saying. The color of methyl orange in an alkali is yellow. At the neutral point or end point, it is actually pink. But the color of methyl orange in an acid is red. Talking about phenolphthalein, the color in an alkali is purple. The color at the end point when all of the acid and the base had reacted is colorless. And also in an acid, the color in an acid is also colorless. Take note of these two. We usually have questions based on them. Also, we have a screen methyl orange, which I've not even seen any question, at least at the GCE level, on this. So, talking about screen methyl orange, it is usually green in alkali solution, and it is gray. It is gray at the end point, and in an acid, it is violet. Talking about acid base titration, depending on the acid or on the base that and on the base we are using, that is what will determine the sort of indicator that we use. When we have a strong acid versus a strong base, we can use any indicator at that point. When we have a strong acid versus a weak base, the ideal indicator is methyl orange. Talking about a strong acid, when we say strong acid like HCl, H2SO4, yes, these are examples of strong acid. But when you talk weak acid, let's say thiazocarbonate 4 acid, ethanoic acid, these are examples of weak acid. You talk of a strong base, you're talking of sodium hydroxide, potassium hydroxide. Talking about weak base, you're looking at something like the carbonate, sodium thiazocarbonate. For this titration, you're looking at something like calcium hydroxide. So, but basically what we're trying to say is that when you have a strong acid versus a weak base, the ideal indicator is your methyl orange. And when you have a weak acid versus a strong base, your ideal indicator is phenolphthalein. And when you have a weak acid versus a weak base, no suitable indicator. Weak acid versus a weak base, no suitable indicator for that. So take note of this, most especially for methyl orange and your phenolphthalein. Take note of the color change. Methyl orange in your alkali is yellow. At the end point, it is pink. So we talk of yellow to pink at the end point. Then your phenolphthalein from purple to colorless. Also take note of the colors in the acids, and that ends that. So that the next thing we want to look at quickly are the calculations that we need to take, so that we want to talk about the various formulas that we are going to need in the course of this. Yes, talking about the calculations, we need to talk about for our titration. Okay, the very starting point is this. In chemistry, normally, just like in normal day-to-day conversations, we talk in things like dozens, which means 12. We talk in packs, In chemistry, we talk in mole. In chemistry, we talk in mole. That is our own language as a chemist. Where dozens talk about 12, in chemistry, mole, 1 mole means 6.02 times 10 raised to power 23 particles. Recall that our particles in chemistry can be atoms, it could be molecules, and it could be ions. Okay, but basically what we are saying is that in chemistry we talk in mole. And of course, every chemistry student, you know that mole equals to mass over molar mass, read as mole equals to mass over molar mass. This is one of the very first formula every chemistry student, and in fact for some science students, the only formula they know in chemistry is mole equals to mass over molar mass. But I think it should go more than that. So stop making me laugh, actually. Stop it. So let's get on. I saw one here getting in the way of my teaching. Okay, now let's get into it. So we said 1 mole equals 6.22 times 10 to the power 23, such that, you know, if I say, okay, I have 3 dozens, 3 dozens will mean 3 times 12, and that's going to be 36. In chemistry, if I say 1 mole contains this, then if I talk number of particles that I can have, number of particles that I can have is how many mole do I have times 6.02 times 10 to the power 23. Imagine I'm having 3 mole. So if I'm looking for the number of particles in it, that will be 3 times 6.02 times 10 raised to the power 23. Invariably, what that means is n equals to 1.806 times 10 raised to the power 24. Yes, that's what 3 times 6.02 is going to give us 18.06 times 10 raised to the power 23. Of course, this is not in standard form, so we try to convert this to standard form by moving the point backwards, and that's why we have 24. But what I'm trying to say here is that aside mole equals to mass over molar mass, it then means, okay, let's my Avogadro's number as stated by Avogadro. This is my Avogadro's number. You recall, if dozens contain 12 pieces in chemistry, when we say 1 mole, it contains this number of particles, and this number is what we call Avogadro's number, so that number of particles is actually mole times, let this represent L, Avogadro's number. The implication of this is that I can also make mole the subject, then mole equals to the number of particles divided by Avogadro's number. So that's another way of looking at my mole. So mole can be mass over molar mass, and at the same time mole can be number of particles divided by Avogadro's number. So at least now you know that it's not every time you begin to say mole equals to mass over molar mass, you can as well say mole equals to number of particles times Avogadro's number. Okay, that's it. Another formula we need to take commit to memory is talking about concentration in chemistry. Concentration. For concentration, you're looking at the amounts. Looking at the amount of solutes in moles or grams in 1 dm cube or 1 liter of solution. So in other words, when we talk about concentration represented as C, let me talk in mole per dm cube, mole per dm cube, which we call here, this is what we call molar concentration. My molar concentration is going to be the amount of solute in mole dissolved in 1 dm cube of solution, so that mole over volume of solution in dm cube, and I'll be right. So what this is read as is concentration equals to number of moles divided by volume. So the implication of this is that if I'm saying concentration in mole per dm cube C equals to NV, then it means I can make number of moles the formula, the subject again, so that the number of moles equals to concentration times volume. So in other words, you can say mole equals to mass over molar mass. You can say mole equals to number of particles divided by Avogadro's number. You can also say mole equals to concentration times volume. So you can see you don't get through all this just by memorizing. You just have to know. But that said, sometimes our volume may be in cm cube, so therefore we have to convert cm cube to dm cube, so that look, 1,000 cm cube makes 1 dm cube or 1 liter. When you try to convert from cm cube to dm cube, you divide. When you try to convert from dm cube to cm cube, you multiply. So that if I have my volume, concentration in mole per dm cube will be mole. If my volume were to be in cm cube, then if my volume were to be in cm cube, let me make this bold. If my volume were to be in cm cube, then I have to convert that cm cube to dm cube by dividing by 1,000. So it means I'd have to divide this by 1,000. And that means 1,000 will then go up, so that my concentration in mole per dm cube at this point equals to mole times 1,000 divided by volume in cm cube. So this goes this way for molar concentration. Yes, for molar concentration, it's actually amount of mole divided by volume in dm cube. If your volume is not given in dm cube, then if it's in cm cube, it means concentration equals to mole times 1,000 divided by volume in cm cube, and you will be correct. So take a look at it again. Our mole can be mass over molar mass. Our mole can be number of particles divided by Avogadro's number. And our mole can as well be concentration in mole per dm cube times volume in dm cube. In mole per dm cube times volume in dm cube. That is for the side to make number of moles the subjects here. So talking about our concentration, they are actually of two types. We have molar concentration, which is what I've talked about here. And then we also have what we call mass concentration. Let me quickly talk about mass. That's concentration in gram per dm cube. In place of my mole here, I am going to be saying mass in grams divided by volume in dm cube. That's what it means. Mass concentration. That's concentration in gram per dm cube. And I'll be correct. So, taking a look at it, concentration in gram per dm cube is mass in gram divided by volume in dm cube, and concentration in mole per dm cube is actually concentration in mole per dm cube is the amount in mole divided by the volume in dm cube divided by volume in dm cube. Now, there is a link between mass concentration and molar concentration. Since mole, if we look at this, mole is mass over molar mass. So let me replace mole with mass over molar mass, so that concentration in mole per dm cube equals to mass over molar mass divided by volume in dm cube. The implication of this is that I'm going to have concentration in mole per dm cube equals to mass over molar mass times volume in dm cube. So that if we look at this very clearly, mass divided by volume in dm cube, what does that represent? Mass divided by volume in dm cube represents concentration in gram per dm cube. What that means is concentration in mole per dm cube equals to concentration in gram per dm cube. In other words, mass over volume in dm cube can be replaced by what? Concentration in gram per dm cube divided by molar mass. This formula is the link between concentration in mole per dm cube, that's molar concentration, and mass concentration. That's the link between them. So which means if I am given concentration of a solution in gram per dm cube and I know the molar mass of that compound, then I can get the concentration in mole per dm cube. At the same time, if I know my concentration in mole per dm cube and I know the molar mass, then I can get concentration in gram per dm cube. This only needs to move here so that it becomes concentration in mole per dm cube times molar mass. Take note of these formulas. I think just about this for now are the things I need in my calculations in for my calculations on that titration. If I know this, at least to a great extent, I will be able to undo those calculations very well. Okay, that said, another thing, I need to talk about is what we call dilution law. Normally, based on what we've said now, that concentration, talking about dilution law. Normally, based on what we've said today, concentration in mole per dm cube represented as C equals to number of moles divided by volume in dm cube. So what that means is that number of moles equals to concentration times volume. In other words, if I am talking about an acid, then it means number of moles of acid equals to concentration of acid times volume of acid. If I am talking base, I can say number of moles of base equals to what? Concentration of base times volume of base. Say if I'm saying number of moles of my acid divided by number of moles of my base, it means I'm saying this divided by this, then I can say this divided by this and I'll be correct. CAVA divided by CBVB. No wonder we then talk of the formula we use for our acid base titration. I'm coming back to dilution law. We then talk of Na over Nb equals to CAVA over CBVB. This formula all takes its roots from our molar concentration. That's why we have what we have. Also take note, let me get proper into my dilution law now. Based on what I am seeing here, it tells me that if concentration is here and the volume is looking inverse here, concentration is inversely proportional to the volume. It means the more water I have, the lesser the concentration. Concentration is inversely proportional to the volume, and that leads me to a point where I talk of CV is always a constant. What this means is that C1 V1 equals to C2 V2, and this is where we talk of dilution law. The product of the concentration and the volume is always a constant. Take for example, if the concentration of a certain solution is 2 moles per dm cube for a volume of 5, if we add more water such that the new volume, this is C1 V1, such that the new volume is now C2 V2, the new volume is now 10 dm cube, then the concentration here, the more the volume, the concentration is inversely proportional to volume. The more the volume, if the volume had increased by a factor of 2, then the concentration will decrease by a factor of 2. It's going to decrease by half. If these are doubled by a factor of 2, 5 times 2, 10, then this will decrease by half. So that what we have 2 divided by 2, that's going to be 1. 2 times 5 is 10, 10 equals to 10. That is why we talk of dilution law. C1 V1 equals to C2 V2. That is, the product of my concentration and volume is always constant. Take note of this. We are going to need this in the course of calculation. Looking at all this, what other formula do we need to be able to solve all of the probable questions we have before us? I think for now we can make do with this. So that talks about all of the formulas we are going to need for this alternative to practical chemistry. Okay, we have a probable question before us, and as you can see on your screen, and B is a solution of sodium triazocarbonate 4. Yes, sodium triazocarbonate 4. But in this case, we're looking at 3.95 gram of sodium triazocarbonate 4 in 750 cm cube solution. In 750 cm cube solution. Okay, let's leave that. As you can see in the question displayed on your screen, we were told that if 22.70 cm cube of the tetrazosulfate 6 acid neutralizes 25 cm cube of sodium triazocarbonate 4. A. Calculate the concentration of B in gram per dm cube. Okay, talking about B, the first thing we were told to calculate in question A, Roman figure 1 here, is the concentration of B in gram per dm cube. And of course, this is very easy. This talks about mass concentration. So you're looking at, okay, the mass divided by the volume in dm cube, as the name implies, gram per dm cube. So you're looking at the mass that you have here. You're dealing with sodium triazocarbonate 4. The mass here is 3.95, but the volume should be in dm cube. Unfortunately, we have 750 cm cube. So if you say 750 cm cube, then this will have to be divided by 1000 to convert it to dm cube. This is in gram. To convert this to dm cube, I'd have to divide this by 1000. And when I divide, the 1000 is going to move up, so that the concentration of B in gram per dm cube is 3.95 times 1000 divided by 750. Computing that, I'm going to get 5.27 gram per dm cube. I've been able to answer question Roman figure 1. Now, question Roman figure 2 says B in mole per dm cube. Yes, they want the concentration of B in mole per dm cube. Remember that I gave us a formula linking concentration in mole per dm cube and concentration in gram per dm cube. Concentration in mole per dm cube is concentration in gram per dm cube divided by the molar mass. Concentration of B in mole per dm cube will therefore be 5.27 gram per dm cube divided. For sodium triazocarbonate 4, if you calculate based on what we were given, we have sodium carbonate. I don't think there is anyone who wants to write this GCE exam and who doesn't know how to calculate molecular mass, but sodium is 23 times 2 as given in the question, plus carbon is 12, oxygen is 16 times 3, that's 46, plus 12 plus 48, that gives you 106 gram per mole. So divided by 106. So therefore, with this, we will be able to convert gram per dm cube to a mole per dm cube as stated in that question. Computing this, we're going to get 0.0497 mole per dm cube. So keep tab of this formula that concentration in mole per dm cube is always concentration in gram per dm cube divided by molecular mass. Okay, we were then told to calculate in Roman figure 3 concentration of A in mole per dm cube. Okay, I wasn't even supplied much information about my A. The only thing I know about my A, okay, looking at even the equation itself as given in the question, sulfuric acid, dilute sulfuric acid, aqueous, to react with sodium triazocarbonate 4 aqueous, we're going to have Na2SO4, Na2SO4, aqueous, Na2SO4, aqueous, and of course, anywhere you have carbonate and an acid is reacting with a carbonate, just know that carbon dioxide gas is going to be liberated. I'm left with H2 here. If I take one oxygen here, add to this, that is water plus carbon dioxide gas liberated. Okay, what this means is that number of moles of my acid is 1, number of moles of my base is 1. Okay, concentration of my base in mole per dm cube, Cb, as calculated in Roman figure 2 is 0.0497 mole per dm cube. I was told in Roman figure 3 to look for the concentration of my acid. That's the question, and from the question I was told that the volume of my base 25 cm cube of sodium triazocarbonate 4, Vb is 25 cm cube, and my Va, average volume of acid juice or average tidal value, was given as 22.70 cm cube. So in this question we were not given a titration table, we were just given figures with which we are to work with. Okay, using that formula, Na over Nb equals to Ca Va over Cb Vb. Since I am looking for my Ca, I can make the Ca the subject. To make the Ca the subject here, this comes here, so that I have my Ca equals to Cb Vb Na divided by Nb divided by Va Nb. If I compute this, my Ca is going to be Cb 0.0497 times Vb is 25 times 1 divided by Va is 22.70 times 1, of course. Nb is 1. If I try to compute this from my calculator, I'm going to get 0.0547 mole per dm cube. That way, I have been able to answer question Roman figure 3 under A, and that ends that. Question Roman figure A4, as you can see on your screen, we were told to calculate A in gram per dm cube. So Ca in gram per dm cube. Don't forget the formula in gram per dm cube. That is going to mean concentration in mole per dm cube divided by molar. Sorry, I'm looking for gram per dm cube, so that's going to be times molar mass. Recall, concentration in mole per dm cube equals concentration in gram per dm cube times molar mass. So if I'm looking for the concentration in gram per dm cube, molar mass just comes here. So I'm dealing with the acid now. Since I know from Roman figure 3 the concentration in mole per dm cube, that's going to be 0.0547 times the molar mass of sulfuric acid is 98 gram per mole. If I compute this from my calculator, I'm going to get 5.36 gram per dm cube. These are very direct calculations. Okay, that is the end of question A. Talking about question B, we were told to calculate the number of hydrozonium ions which could be obtained from the result in 183. The result in 183 is talking about the concentration of my sulfuric acid. So when you look at it, H2SO4 aqueous. Normally, what this means, if I dissociate this, means 2H plus aqueous plus SO4 2 minus. Since I am talking about the number of hydrozonium ions, hydrozonium ion here means H3O plus. Since I have two hydrogen ions, it's same as saying 2 moles of hydrozonium ion. So what this means is that 1 mole of H2SO4 is stoichiometrically equivalent to 2 moles of hydrozonium ion. So that if I say 1/2, that's 1/2, then the concentration of the or to look for number of hydrozonium ions here, so that since the number of moles of the acid, as you can see, 0.057 mole, 0.0547 mole, then what will be the mole of hydrozonium ion? See, 1 to 2. Then since the mole of H2SO4 that I have per dm cube here is 0.0547 mole, then how many moles will my hydrozonium ion be? So 1 to 2, then mole of this divided by the mole of this. So the mole of hydrozonium ion is actually 2 times 0.0547 mole, and that is going to give me, if I compute from my calculator, okay, this is going to give me 2 times 0.0547. So number of H3O plus ions is always mole. Number of particles is always mole times Avogadro's number. That is why at the end of the question we're given Avogadro's constant. So this is the number of moles of my hydrozonium ion. So this is 2 times 0.0547 times Avogadro's constant 6.02 times 10 raised to the power 23. If I compute this together for my calculator, I am going to have 0.659. Yes, 0.659 times 10 raised to the power 23. If I move this, this will be 6.59 times 10 raised to the power 22. If I had moved this forward, then this will be minus 1 ions. So that is the number of hydrozonium ions that would have been formed from A3, and that ends question B. On question C states, state a possible indicator for the reaction. Of course, this question is between sulfuric acid, H2SO4, and sodium thiazocarbonate. This is a strong acid, this is a weak base. For a strong acid versus a weak base, the suitable indicator here is methyl orange. Suggest a possible indicator for the reaction. Well, a suitable indicator for this reaction is methyl orange. We were told to give reason. The reason is very simple. It's a strong acid versus a weak base. So what we use is methyl orange. So that ends that. And with that, we've come to the end of that probable question. I know some of you might be finding it difficult dealing with question B because it involves a bit of stoichiometric equivalent. Okay, but not to worry. In the course of our UTME preparation, we're going to deal with the whole of stoichiometry head on, talking about what we call key door concept under stoichiometry. But look at it very well. H2SO4 Normally, when dissociated, will give us 2 moles of hydrogen ion. Hydrogen ion here means hydrozonium ion. It can be used interchangeably. So having 2 moles of it, so it means 1 mole of H2SO4 gives me 2 moles of hydrozonium ion. So 1 to 2, 1 to 2, then mole of this divided by mole of this. That's what we have. So if we equate that, mole of the hydrozonium ion gives me 2 times 0.0547, and having the mole of that, I can now say number of ions equals to mole times Avogadro's constant to get this. So with that, we've come to the end of this, and do comment, like, subscribe, and turn on the notification bell, and check us out on our website at www.300plusacademy.com. Link up with us on WhatsApp so that you can ask us questions on gray areas where you need more clarity, and I tell you, we will attend to your needs so that you ace your next exam. From me to you, it's bye for now.